In 2013, astronomers discovered something that shouldn't exist. A structure so massive, so impossibly large, that according to our best cosmological models, it would take longer than the age of the universe itself to form. 10 billion light-years across. That's roughly 1/10 of the entire observable universe, contained in a single structure, and it's not alone. Today, we're exploring the cosmic anomalies that are forcing scientists to question everything we thought we knew about the universe. Objects behaving in ways that defy explanation, measurements that contradict each other at the most fundamental level, structures that simply shouldn't be there. These aren't fringe theories or pseudoscience. These are peer-reviewed observations that have left even the brightest minds in physics searching for answers. If you're ready to see how far the edges of scientific knowledge truly extend, stay with me. I'm here to take you on a journey through some of the most perplexing observations in modern astronomy. And I want to be clear from the start, these aren't conspiracy theories or science fiction. Every anomaly we'll discuss today comes from peer-reviewed research, documented by some of the most sophisticated instruments humanity has ever built. Over the next 20 minutes, we're going to explore 3 categories of cosmic mysteries. First, structures that break the fundamental rules of cosmology, things that are too big, too empty, or too organized to exist according to our current models. Second, objects behaving in ways we simply cannot explain. Visitors from interstellar space that accelerate without any visible means of propulsion. Bursts of energy so powerful they outshine entire galaxies in milliseconds. And third, contradictions in our most basic measurements of the universe itself. Numbers that should match but don't, forcing us to question whether we understand reality as well as we thought. But here's what makes this truly fascinating. These mysteries don't represent failures of science. They represent frontiers. They're the places where our next great breakthroughs are waiting to happen. Because throughout history, every major scientific revolution began with someone noticing that something just didn't fit. So let's start with what we think we know, before we explore what doesn't make sense. Before we dive into what doesn't make sense, we need to establish what we think we know about the universe. The standard model of cosmology is our best description of how the universe works. It tells us that the universe is approximately 13.8 billion years old. It's expanding, and that expansion is actually accelerating. Matter and energy are distributed relatively uniformly on the largest scale, and cosmic structures, from galaxies to massive galactic clusters, formed gradually through gravitational collapse over billions of years. This isn't just theory, it's backed by decades of observations. The cosmic microwave background, the afterglow of the Big Bang itself, galactic surveys mapping billions of light-years of space, measurements of distant supernovae showing us how the universe has evolved. One of the foundational principles is called the cosmological principle. It states that on sufficiently large scales, the universe should look roughly the same everywhere. No matter where you are, no matter which direction you look, the large-scale structure should be homogeneous and isotropic. Think of it like looking at a pointillist painting. Up close, you see individual dots, but step back far enough, and it all blends into a uniform image. According to our calculations, this uniformity should emerge at scales larger than about 1.2 billion light-years. Beyond that distance, the universe should appear smooth and evenly distributed. We also understand fairly well how structures form. In the early universe, tiny quantum fluctuations were stretched by cosmic inflation. Over time, gravity amplified these fluctuations. Matter clumped together, first into stars, then galaxies, then clusters of galaxies, connected by vast filaments of dark matter. This process takes time, lots of time, and there are limits to how quickly structures can grow, based on the age of the universe and the laws of physics. These are the rules. And yet, when we look closer, we keep finding things that break them. Meet the largest known structure in the observable universe, the Hercules Corona Borealis Great Wall, a cosmic filament of galaxies stretching across 10 billion light-years of space. To put that in perspective, if you could travel at the speed of light, it would take you 10 billion years just to cross from one end to the other. That's about 1/10 of the entire observable universe contained in a single structure. Now, here's the problem. Remember that cosmological principle we just discussed. it. The idea that the universe should be uniform at scales larger than 1.2 billion light-years. This structure is 8 times larger than that theoretical limit. It's not just slightly over the line. It's so far beyond what our models predict that its very existence challenges one of the foundational assumptions of modern cosmology. But it gets worse. Structure formation takes time. Gravity works gradually, pulling matter together over cosmic timescales. Based on our understanding of how the universe evolved, we can calculate how long it would take for a structure of this size to form through gravitational collapse. The answer? Longer than the universe has existed. Think about that for a moment. Imagine you have a recipe that says your cake needs exactly 30 minutes to bake. You set the timer, you follow the instructions perfectly, but somehow you open the oven after just 15 minutes and find a fully baked, elaborately decorated wedding cake sitting there. That's essentially what we're seeing. A structure that, according to our best physics, shouldn't have had enough time to form. So what do we do with this? Well, scientists haven't thrown out the cosmological principle. That would be premature. Instead, they're exploring several possibilities. One hypothesis is that we're observing a projection effect. Maybe what looks like a single massive structure is actually several smaller structures that happen to align from our perspective. Imagine holding a string of beads at arm's length. From certain angles, they might appear to form a solid line, even though they're actually separated in three-dimensional space. Another possibility is that our models of structure formation need revision. Perhaps there are mechanisms in the early universe that we don't fully understand, ways that matter could have clumped together more efficiently than our current theories predict. Some cosmologists have even suggested that this could indicate unknown forces or fields at play during the universe's infancy, something that gave certain regions a head start in structure formation. What's important to understand here is that scientists aren't panicking. They're not abandoning decades of cosmological theory because of one observation. But they're also not dismissing the observation because it doesn't fit the theory. This is how science actually works. You have a model. It explains most things beautifully. Then you find something that doesn't quite fit. You don't immediately assume the model is wrong, but you also don't ignore the anomaly. You investigate. You look for alternative explanations. You gather more data. You refine your instruments. You consider possibilities you hadn't thought of before. And sometimes, if enough anomalies accumulate, you realize that your model needs fundamental revision. The Hercules Corona Borealis Great Wall stands as a monument to how much we still don't understand about cosmic evolution. It's a reminder that the universe is under no obligation to conform to our expectations. But cosmic megastructures aren't the only things breaking the rules. While some parts of the universe are impossibly full, others are impossibly empty. In 1981, astronomer Robert Kirshner and his team were conducting a survey of galaxy distributions when they found something deeply unsettling. A void, not just any void, but a spherical region of space 330 million light-years in diameter that was almost completely empty. The Boat's void, sometimes called the Great Nothing, contains only about 60 galaxies. For comparison, a typical region of space that size should contain around 2,000 galaxies. Imagine dropping a handful of sand on a table. You'd expect it to spread somewhat evenly, with natural clumps and gaps forming randomly. Now imagine finding an area the size of a dinner plate with only 3 grains of sand on it. Not because you carefully placed them there, but because that's just how they fell. That's what the Boat's void represents. An enormous region of space that's inexplicably, almost impossibly empty. Now, voids themselves aren't unusual. They're actually a natural consequence of cosmic structure formation. As matter clumps together under gravity to form galaxies and clusters, it leaves behind emptier regions. Our models predict this. We see it everywhere. But voids this large, this empty, that's where things get problematic. According to our understanding of how dark matter and dark energy shape the universe, voids can form, but they shouldn't reach this scale without containing more matter. The gravitational influence of surrounding structures should have pulled at least some galaxies into this region over billions of years. So why is it so empty? Some researchers have proposed that voids might grow faster than our models predict. As galaxies move away from the center, the expansion of space itself could amplify the emptying process. Think of it like a feedback loop. The emptier it gets, the less gravitational gravitational attraction there is to slow things down, so it empties even faster. Others suggest that the boat's void could be evidence of exotic physics in the early universe. Perhaps variations in dark energy density created regions that resisted structure formation more strongly than we thought possible. There's even speculation about whether these supervoids could affect our measurements of cosmic expansion. Light passing through such empty regions might behave slightly differently than light traveling through denser areas, potentially skewing our observations. The truth is, we don't have a definitive answer yet. The boat's void remains one of the largest and most perplexing structures, or rather lack of structure, in the known universe, a cosmic question mark floating in the darkness. And it forces us to ask, if our models can't fully explain the distribution of matter on these scales, what else might we be missing? Now, you might be thinking, if these structures break our models, doesn't that mean our science is wrong? Not quite. And this is where understanding how science actually works becomes crucial. Science isn't about having all the answers. It's about having a method for finding better answers. When we encounter something that doesn't fit, that's not failure. That's opportunity. Every major breakthrough in physics has come from noticing something that didn't quite match our expectation. And sometimes, the most perplexing anomalies aren't massive structures light years away. Sometimes they're visitors that come right to our doorstep. October 19, 2017. An object enters our solar system, but it's not from here. In fact, it's the first confirmed interstellar visitor we've ever detected. Astronomers named it Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, and its behavior has been keeping scientists up at night ever since. When we first spotted Oumuamua, it was already on its way out of the solar system, moving at roughly 87 kilometers per second. We only had a brief window to observe it before it disappeared back into interstellar space. What we saw during that window was strange. First, its shape, based on how its brightness varied as it tumbled through space. Astronomers calculated that Oumuamua was extremely elongated, somewhere between 5 and 10 times longer than it was wide. Think of a cigar, or perhaps a pancake viewed edge-on. Either way, nothing like the typical asteroids or comets we're used to seeing. But the shape, while unusual, wasn't the real mystery. The real mystery was its acceleration. As Oumuamua swung around the sun and headed back out into deep space, it sped up, not just from the sun's gravity, but from something else, an extra push that our models couldn't account for. Now, this kind of acceleration isn't unheard of. Comets do it all the time. As they approach the sun, ice on their surface vaporizes, creating jets of gas that act like tiny rocket engines. This outgassing creates the characteristic tail of a comet and provides a small but measurable thrust. Here's the problem. We detected no outgassing from Oumuamua. None, no tail, no jets, no detectable emissions of gas or dust. And yet, it was accelerating as if something was pushing it. The scientific community has been grappling with this ever since. One hypothesis suggests that Oumuamua could be made of frozen hydrogen. Hydrogen ice would be so cold and would vaporize so diffusely that our instruments might not detect it. It would be essentially invisible outgassing. The math works, but we've never seen a hydrogen iceberg in space before, so we don't know if they can even form or survive the journey through interstellar space. Another idea proposes that Oumuamua might have an exotic dust composition that interacts with sunlight in unusual ways, creating pressure that could account for the acceleration. Again, possible, but speculative. And then there's the hypothesis that generated the most headlines. Harvard astronomer Avi Loeb suggested that we should at least consider the possibility that Oumuamua could be artificial, a light sail, perhaps, technology from another civilization tumbling through the galaxy. Now, to be absolutely clear, most scientists consider this extremely unlikely. The natural explanations, while incomplete, are far more probable. We don't need to invoke alien technology when we might simply be observing a type of object we've never encountered before. But here's what's remarkable about this debate. The scientific community is willing to put even unconventional ideas on the table when the data demands it. That's not weakness. That's intellectual honesty. We don't know what Oumuamua was. We probably never will. It's long gone now. tumbling through the darkness between stars, and we don't have the technology to catch up to it. What we do know is that the universe is full of surprises, and sometimes those surprises arrive without warning, challenge everything we think we understand, and disappear before we can find the answers. But at least Oumuamua was a single object, a lone mystery. What happens when the mystery repeats itself? When signals from deep space burst into existence, over and over, without explanation. Imagine your radio suddenly picks up a signal. It lasts milliseconds, just a few thousandths of a second. But in that brief flash, it releases as much energy as the sun produces in several days, and it comes from billions of light years away. Then it's gone. These are fast radio bursts, and they're one of the most perplexing phenomena in modern astronomy. The first FRB was discovered in 2007 by astronomer Duncan Lorimer, who was analyzing archival data from the Parkes radio telescope in Australia. The signal was so brief, so intense, and so unexpected that it took years before the scientific community was convinced it was real and not just a glitch in the equipment. Since then, we've detected hundreds of them. Most fast radio bursts occur once and never repeat. They flash into existence, dump enormous amounts of energy into space, and then vanish forever. We have no way of predicting when or where the next one will appear. We don't know what creates them. The theories range widely: neutron-star collisions, magnetar flares, evaporating black holes. Some have even suggested, though this is considered highly unlikely, that they could be technosignatures from advanced civilizations beaming energy across vast distances. The problem is that each explanation has issues. Most cataclysmic events that could produce this much energy in such a short time would destroy the source, which would explain why most FRBs don't repeat. But then there's FRB 121102. This particular fast radio burst broke all the rules. It repeated, not regularly, but multiple times over several years. And when astronomers finally traced it to its source, they found it was coming from a dwarf galaxy 3 billion light-years away, in an environment unlike anything we'd expect. A repeating FRB suggests a mechanism that can fire multiple times. That eliminates most catastrophic explanations. Whatever is creating FRB 121102 survives the process and can do it again. This was a game changer. Then, in April 2020, something extraordinary happened. Astronomers detected a fast radio burst from within our own galaxy. It came from a known magnetar, a type of neutron star with an incredibly powerful magnetic field, about 30,000 light-years away. This was huge. For the first time, we had confirmed at least one possible source of FRBs. Magnetars could produce them. Problem solved. Right? Not quite. While this discovery explained some fast radio bursts, it doesn't explain all of them. The local FRB was much weaker than most of the distant ones we've detected, and it doesn't fully account for the repeating patterns or the strange environments some FRBs are found in. So we're left with a partial answer. We know magnetars can produce FRBs, but we suspect there might be multiple types of sources creating similar signals through different mechanisms. This is how science works in real time. One mystery partially solved, revealing deeper questions underneath, each answer leading to new puzzles. And speaking of puzzles, some anomalies aren't about weird objects in space. Some are about contradictions in the very fabric of reality itself. Measurements that should agree but don't, numbers that are forcing us to question whether we understand the universe as well as we thought. Some of the most troubling anomalies in cosmology aren't about strange objects. They're about contradictions in our most fundamental measurements. The Hubble tension is one of them. Here's the issue. We have two different methods for measuring how fast the universe is expanding. Both methods are sophisticated, precise, and backed by decades of refinement, and they give us different answers. The first method uses the cosmic microwave background. This is light from the very early universe, released about 380,000 years after the Big Bang. By analyzing the patterns in this ancient light, we can calculate the expansion rate of the universe. This method gives us a value of about 67 kilometers per second per megaparsec. The second method uses local distance measurements. We observe supernova and special pulsating stars called Cepheid variables in relatively nearby galaxies. These objects have known brightness, so by measuring how dim they appear, near, we can calculate their distance. By tracking how fast these galaxies are moving away from us, we determine the expansion rate. This method gives us a value of about 73 kilometers per second per megaparsec, 67 versus 73. That might not sound like much, but in cosmology, it's massive. These two measurements should give us the same answer. They're measuring the same thing, the expansion rate of the universe. The difference is beyond what measurement error can explain. Statistically, the discrepancy is highly significant. It's like measuring the same room with two different tape measures and getting results that differ by several feet. Something is fundamentally wrong. So what's going on? There are several possibilities, none of them simple. One option is systematic error. Maybe there's something we're not accounting for in one or both methods. Perhaps dust is affecting our observations in ways we haven't recognized. Maybe our cosmic distance ladder, the series of measurement techniques we use to calculate vast distances, has a flaw somewhere. But scientists have been checking and rechecking for years. The discrepancy persists. Another possibility is new physics. Maybe dark energy, the mysterious force driving cosmic acceleration, behaves differently than we thought. Perhaps it was stronger in the early universe and has changed over time. Some physicists have proposed exotic solutions, early dark energy, new types of particles that we haven't detected yet, modifications to general relativity itself at cosmic scales. Or maybe, and this is the most unsettling possibility, our entire model of cosmic evolution needs fundamental revision. As of now, this remains unresolved. Thousands of scientists are working on it. New telescopes are being built specifically to help address this question. The James Webb Space Telescope is already providing more precise measurements, but the tension hasn't gone away. If anything, better data has made it more pronounced. This is what it looks like when science encounters something truly challenging. Not a simple anomaly that can be explained away, but a deep contradiction that suggests our understanding might be incomplete at a very fundamental level. And there's one more anomaly we need to discuss. One that's been hiding in plain sight since we first mapped the afterglow of the Big Bang itself. The cosmic microwave background is the oldest light in the universe. A snapshot of what the cosmos looked like when it was just 380,000 years old. According to our models, it should be almost perfectly random. Tiny fluctuations, yes, but distributed uniformly across the sky with no particular pattern or direction. But it's not. When scientists analyzed the large-scale patterns in the CMB, they found something deeply unexpected. Certain features appeared to align with each other. And even more bizarrely, they seemed to align with the plane of our solar system. This pattern was nicknamed, somewhat tongue-in-cheek, the axis of evil. Now, understand what's strange about this. The cosmic microwave background is a relic from when the universe was 380,000 years old. Our solar system formed about 9 billion years later. There should be absolutely no correlation between ancient cosmic patterns and the orientation of our local solar system. And yet, there appears to be one. Several features in the CMB, including what's called the quadrupole and octupole moments, show this unexpected alignment. It's as if the early universe somehow knew about the plane of our solar system billions of years before it would exist. Obviously, that doesn't make sense. So what could explain this? One possibility is that it's a statistical fluke. When you analyze enough data, sometimes you find patterns that look meaningful but are actually just random chance. The human brain is exceptionally good at finding patterns, even when none truly exist. Another possibility is instrumental error. Maybe there's something about how we observe the CMB, some systematic effect from our instruments or our location in the galaxy that's creating this apparent alignment. But scientists have been checking for this. Multiple satellites, multiple instruments, multiple analysis methods. The pattern persists. The most intriguing possibility is that this represents something fundamental about the universe's geometry or topology that we don't understand. Maybe the universe isn't quite as isotropic as the cosmological principle assumes. Maybe there are large-scale structures or features that violate our expectations of cosmic symmetry. Some cosmologists think it's noise, an artifact that will disappear with better data. Others believe it's a genuine anomaly pointing toward new physics. As of now, The axis of evil remains one of the most debated topics in cosmology, a pattern that shouldn't be there, stubbornly refusing to go away. It's a reminder that even our most fundamental observations, the ones we build entire cosmological models upon, might contain surprises we haven't fully grasped yet. So here we are, 6 anomalies, 6 cracks in our cosmic understanding, structures that shouldn't exist, objects that defy explanation, measurements that contradict each other, patterns that violate our most basic assumptions about the universe. Now, I want to address something important. When I share these mysteries, some people worry that I'm trying to undermine science or suggest that we don't know anything, that we're just guessing, that all our cosmological theories are wrong. That's not the point at all. Here's what these anomalies actually reveal. First, science is not a collection of facts. It's a process, a method for continuously refining our understanding. When we find something that doesn't fit, that's not science failing. That's science working exactly as it should. Second, the greatest breakthroughs in history came from anomalies. Mercury's orbit didn't quite fit Newtonian physics. That discrepancy led Einstein to general relativity. Black body radiation didn't fit classical physics. That puzzle gave birth to quantum mechanics. Every revolution in understanding began with someone noticing that something just didn't add up. Third, admitting we don't know is not weakness. It's intellectual honesty. It's the foundation of genuine scientific inquiry, and it's the first step toward actually knowing. These anomalies aren't threats to science. They're invitations. They're frontiers where the next generation of discoveries await, where textbooks will be rewritten, where Nobel Prizes are waiting to be won, where our understanding of reality itself might fundamentally shift. The universe is under no obligation to make sense to us. It doesn't care about our models or our equations or our expectations, and that's not a problem. That's what makes the pursuit of knowledge so extraordinary. Let's recap what we've explored today. We've seen structures that dwarf anything our models predicted could form in the age of the universe. Voids so empty they challenge our understanding of cosmic evolution. An interstellar visitor that accelerated without any visible means of propulsion. Bursts of energy from across the cosmos that we still can't fully explain. Measurements of the universe's expansion that contradict each other at the most fundamental level, and patterns in the oldest light in existence that shouldn't correlate with anything in our local cosmic neighborhood. 6 anomalies, 6 mysteries that remain unsolved. So what does this mean for science? It means we're living in one of the most exciting eras in the history of astronomy. Every one of these anomalies represents a potential breakthrough waiting to happen. A question that, when answered, will reshape how we understand the cosmos. And what can you take from this? Whether you're a student considering a career in science, an enthusiast who simply loves learning about the universe, or someone who stumbled upon this video out of curiosity, there are lessons here. First, stay curious. The most important discoveries come from asking, what if this doesn't fit? The people who change our understanding of reality are the ones willing to look closely at the things that don't make sense. Second, embrace uncertainty. The edge of knowledge isn't a flaw in science. It's where the most interesting things happen. It's where we're reminded that there's still so much to discover. Third, think critically. Science isn't about accepting authority. It's about demanding evidence, questioning assumptions, and being willing to revise your understanding when new information appears. But it's also about recognizing the difference between healthy skepticism and rejecting evidence simply because it's uncomfortable. The universe is far stranger, far more complex, and far more wonderful than we ever imagined. These anomalies aren't problems to be solved and forgotten. They're windows into aspects of reality we haven't glimpsed yet. They're reminders that despite everything we've learned, despite all our technological advancement and theoretical sophistication, we're still just beginning to understand the cosmos we inhabit. And that's not a failure, that's an adventure. If this journey through cosmic mysteries fascinated you, consider subscribing. We explore the edges of scientific knowledge, where certainty ends and wonder begins. I have a question for you. Which of these anomalies intrigued you most? Was it the impossibly large structures, the mysterious interstellar visitor, or maybe the contradictions in our most fundamental measurements? Let me know in the comments. I read them. and your input helps shape future videos. And if you want to dive deeper, I've compiled a list of research papers and scientific articles in the description. These aren't simplified summaries. They're the actual work from the scientists studying these phenomena. If you're ready to explore beyond what we covered today, those resources are waiting for you. Thanks for joining me on this journey to the frontiers of the known universe. Until next time, keep looking up and keep questioning.